Hi everyone, welcome back. I'm Debusattam and you're watching the fifth lecture of EE635 Applied Linear Algebra. This happens to be the second module. So at the end of the last module, we defined two concepts called row span and column span of a matrix, right? We will see how to find basis of these row span and column span, right, in this module. Okay, for that, I have to share my screen. Let's hang on for a bit. It should be up anytime. Let's see. Okay, here it is. Now, suppose we have a matrix, yeah, which is a matrix in if we don't need real numbers anymore, we can make do with any field M cross N, right? So, so let me write this topic as row span and column span. Okay, right. So A is an M cross N matrix whose entries are coming from the field F. Okay, so A can then be written as, of course, as you know, A11, A12. I never get tired of writing this matrix. A21, A22, A2N, and so on up to AM1, AM2 to AMN, right? Of course, you can view these rows, this matrix, as a collection of rows. You can also view this matrix as a collection of columns, right? Okay, so row wise, suppose I'm writing A as R1, R2, and so on up to Rm. How many rows are there? M number of rows are there. Here, each of these rows, R1, R2, all of these are up to Rm. All of them, remember, are elements of F1 cross N. So these are N-sized row vectors. Okay. So therefore, row span of A or RSP of A, by definition, this is another name for row span. Row span of A is by definition the span of R1 dot 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 up to Rm. Is this all right? This, of course, is going to be being a span. It's going to be a subspace of F1 cross N. So the space of rows of numbers coming from the field F, right? Rows having size n. So the row span is a subspace of this vector space. Similarly, column wise, I can write A as C1, C2, dot 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 up to Cn, where each of these C1, C2, these guys are elements of F. I may just write M, right? M means M cross 1, as we have seen before, right? So these are all columns of vectors. So of course, now CSP of A, which is nothing but another name for the column span, which we also write as col span of A, is by definition the span of C1, C2, dot 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 up to Cn. This, of course, as you can say, is a subspace of Fm. So thus we have two such subspaces, right? Now, given a matrix A, let's say I ask the question, how do I get a basis for row span of A? I'll do row span, column span you'll do, right? You'll do yourself. But before that, before I delve into this matter, let me tease you with one particular question, which is a question that I want you guys to think about, but I'll give you an answer to this question at the end of this module. The question is the following. You know, the zero vector, I mean the set that contains only the zero vector is a subspace, right? What is its dimension? And which basis will span it? Of course, it has a generating set, zero vector itself is a generating set. But see, zero is not linearly independent, right? Yeah, it cannot be linearly independent because we have already seen that any collection that contains the zero vector is linearly dependent by default. This cannot be linearly independent. So then how do I get a basis? So think about this while we talk about think while we talk about this case of finding out basis for a row span. Okay. Now we first notice the following. Remember that observation that we did long back in the second lecture, that if there is a matrix A, and suppose that matrix is multiplied by a row vector like this, say alpha transpose, where let me not write alpha transpose, let me just write this thing up, alpha 1, alpha 2, dot up to alpha m. Yeah, this multiplies A. This is a well-defined multiplication, and the L and the the result of this multiplication is also an element from F1 cross N. Yeah, this is a linear combination of elements in A. So that means this is a typical element of the row span of A. Okay. Now, suppose I have A and I do this row operation. Remember, I do some row operation and I get M times A, which I'm calling, say, A hat. I did some row operation and changed this to A hat. Remember, this M was invertible, right? Yeah, M is always square invertible. M belongs to F M cross M. M is invertible. We have seen before. These are products of elementary row operation matrices, so they are always invertible. Now, in this scenario, I make the following claim, and you verify whether this is true or not. Row span of A must then be equal to row span of A hat. Think about this. This has to be true. Why? Well, once again, I have to prove equality of two sets. So I better do it by showing that one set is contained in the other. So first of all, let us try and check whether row span of A is contained in the row span of A hat or not. Okay, what do I have to do for that? So what should I use? Let V. Okay, let me not write V. Let me use this because row use R. So let R be a typical element of row span of A. This implies there exists alpha 1 dot up to alpha m, which is an element in F1 cross M, such that, so let me call this as alpha, such that alpha A must be equal to R, right? That is how row span is defined. It's a linear combination of the rows. Remember the observation in the second lecture? This product means linear combination of the rows, right? So this alpha I must be equal to R. Now, define, okay, yeah, right. Now note that A hat is equal to M times A, which means A must be equal to M inverse A hat. So I write this as this is equivalent to alpha M inverse A hat must also be equal to R. But then define alpha hat as alpha m inverse. Of course, this is also an element in F1 cross M, because M inverse is an M cross M invertible matrix, is alpha hat. So then this implies, this is if and only if R is equal to alpha hat times A hat, which is of course an element in RSP A hat, right? That is what we wanted to prove. The other way is in fact easier. We have to prove that RSP of A hat is contained in RSP of A. But you see, I'll do it short. I'll do it now, I'll do it quickly. Let alpha be in F1 cross M such that, okay, I'm sorry, let R in RSP A hat be arbitrary. This implies there exists alpha hat in F1 cross M such that alpha hat A hat equals R hat. This implies if and only if alpha hat M A is equal to R hat. This is if and only if alpha A is equal to R hat, which then obviously belongs to RSP of A, where alpha is defined as alpha hat times M. That's it. That's the end of the proof. So the two row spans are equal. So then what this essentially means, this means, you see, when we are doing this row reduction by doing elementary row operations, the row span of the matrix A remains invariant. It doesn't change, right? So that means if I have a matrix A, then by a series of row operations, finally it converts to R, which is an RRE of A. Then row span of A is equal to row span of the RRE matrix R, right? But what is so special about this RRE matrix? Yeah, it turns out that the rows of R forms a basis of row span of R, which is equal to the row span of A. So then actually obtaining this row reduced echelon form, what we were doing essentially was we were trying to find a basis for the row span of A. Yeah, the subspace that is spanned by the rows of A, we were actually trying to find out a basis, and that basis is given by this, the rows of the row reduced echelon form. And indeed, why is this true? First thing, so suppose R is equal to, what should I write? Say epsilon 1, epsilon 2, up to epsilon R. Yeah, these are the non-zero rows, and then all zeros. Yeah, this is a row reduced echelon form of R. Yeah, these are non-zero rows. Okay, now in this epsilon 1 up to epsilon R, of course we know that span of these vectors E1 up to ER is equal to row span of R, and of course, as we have seen before, this is row span of the original matrix A. So then that the fact that they span is okay. A zero vector span is just zero, so they don't add anything extra. So therefore we can just go ahead and neglect those zero rows. Okay. So E1 up to ER must be a generating set. Yeah. Now when will it turn out to be a basis? Well, of course, if they are linearly independent, but then it has to be true. Why? Let me do this. So to show that E1 up to ER is linearly independent. For that purpose, consider a linear combination of E1 up to ER. I mean epsilon 1 up to epsilon r. So what is that? Alpha 1 epsilon 1 plus alpha 2 epsilon 2 plus dot 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 up to alpha r epsilon r. And suppose this is equal to 0. Okay. Now, how does epsilon 1 look like? Remember, epsilon 1 would look something like this. There will be some zeros initially, then there will be a leading one appearing at the k1th position or k1st position. Then there could be zero non-zero entries, we don't know. But of course, it was guaranteed that all the other k positions, that is k2 and so on, yeah, up to kr, there will be zeros. Everything else could be zero non-zero. Okay. Similarly, epsilon 2 will have a 1 at the k2th position. For all the other k positions, it will be 0. But everywhere else, it will be unknown. Now, from there, let me just try and appeal to your imagination and let me clarify what would be the next step. The next observation is that in this linear combination, then from this structure of the epsilon vectors, this linear combination, it therefore follows, that, listen to this very carefully. This is the most crucial argument of this whole process. Alpha 2 epsilon 2 plus dot 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 up to alpha r epsilon r is equal to 0. This is the same as, so this vector now is going to be, I don't know what these positions may be, I mean what these entries may be, whatever they are, but I can say this one for sure, that at the kth position alpha 1 will appear, at the k second position alpha 2 will appear, and so on. So in this linear combination, the alpha 1 in this linear combination gets multiplied to the leading one at the k1st position, in the k1 position, and in that k1 position nothing else appears. So only that alpha 1 will be there in the linear combination at the k1 position, right? At the k2 position alpha 2 will appear, at the k3 position alpha 3 will appear, and so on. This is at k1, this is at k2, and so on. And this is equal to 0. But if this vector is equal to 0, then every entry must be 0. Yeah, these vectors are, I mean, the 0 vector in f1 cross n is the all 0 vectors. Every entry is 0. So therefore, this implies alpha 1 must be 0, alpha 2 must be 0, and so on up to alpha r must be 0. But that means it's the trivial linear combination. So I assume that a linear combination of epsilon 1 up to epsilon r goes to 0. That implies only the trivial linear combination goes to 0, which means epsilon 1 up to epsilon r must be linearly independent. So this implies epsilon 1 dot 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 up to epsilon r is linearly independent. And that is what we wanted to prove. So this is a basis, right? So now, same thing applies to column span. So somebody gives you a collection of vectors and tells you, okay, look at the span of these vectors, which are columns of numbers. Find me a basis for this subspace of this span. What will you do? We'll do elementary column operations and we'll obtain a column reduced echelon form. Then those non-zero columns of that column reduced echelon form will give you a basis of that column span, right? So that's how you get that's how you get basis of given spans of vectors. Now this also is important for us from another point of view. You see, we have been alluding to this number, right, of non-zero rows in a row reduced echelon form. So then this number small r, which happens to be the number of non-zero rows in R, that then is equal to dimension of the row span of the matrix A over the field. Yeah, is it all right? So this dimension is then called the row rank of the matrix A. And similarly, when you work this out, number of non-zero, work this out for columns, non-zero columns in a column reduced echelon form of A must be equal to dimension of the column span of A, and that is called that is defined as the column rank of A. The fact that these two ranks are equal will be the subject of a later lecture. We'll do that very soon. But now the discussion is up to this much. Yeah, think about this. I think an immediate attention problem will be there. Well, you'll be asked to find out such basis, but if not, then you'll be asked to find out such things in a homework problem very soon. Okay, now getting back to that interesting question that I had asked. What is a basis for the zero subspace? What will it be? What will it be its dimension? What is the dimension of the zero space? So intuitively, what should be the dimension? Zero, right? Because it's just a point. Think of the Euclidean space. In the Euclidean space, if you look at the zero vector, that's the origin, that's a single point. What should be its dimension? Zero, right? One dimension is a line, two dimensions is a plane, three dimensions is a space. Yeah, just a single point must be zero dimension. But zero dimension would mean, from this point of view, what? That its basis must contain zero elements. Yeah, what does that mean? Which set contains zero elements? Zero element means no elements is there. That means it's an empty set. Yeah, and indeed, span of the empty set is the zero subspace. Sounds odd, but empty set is vacuously linearly independent because there is nothing to check for linear independence. There is no vector at all. Therefore, it's linearly independent. Now, if it is linearly independent, and why should its span be the zero space? Well, once again, go back to that earlier definition. You may be asking that span is easy to understand. Why did we have to go to this weird definition of defining span as, you know, the smallest subspace that contains the given set? So here the given set is empty. Suppose the given set is empty. Now, which subspace will contain it? Every subspace, all possible subspace will contain it. And what is the intersection of that? The intersection of all possible subspaces is the zero subspace. So that means the zero subspace is the smallest subspace that contains the empty set. And from that definition, then the span of empty set is indeed equal to the zero subspace. So that's the basis for the zero subspace. So on this thought, let me call it an end to this module. We'll meet for the next module very soon once you are done with solving these immediate attention problems, namely immediate attention problem number 4, which is this one. So we are defining two subspaces here. First, you have to check that these are subspaces of 2 by 2 matrices. So look at 2 by 2 square matrices. Look at these, the matrices of this particular structure of x minus x, y, z, where x, y, z are arbitrarily chosen, and a, b minus a, c, where a, b, c are arbitrarily chosen from the field. Find out the dimensions of W1, W2, W1 plus W2, and W1 intersection W2, right? And then a difficult, not so difficult, but something that will require you to think, immediate homework problem, that if you view the set of real numbers as a vector space over the set of rational numbers, which is a field, then this vector space is infinite dimensional. So we have already defined dimension. Think about this one. Yeah. And then let's come back and meet for module number 3 of the 5th lecture. Okay. Till then, bye bye.